Okay, hello everyone. Thank you very much for coming to today's AIAA Los Angeles Las Vegas section special event. Today I have a really exciting program. You'll learn a lot of things. It's very exciting. And while we're waiting for more people to join in, let me try to briefly say something logistically and also for welcoming everyone. So let me see. Okay, so basically, we really appreciate the AIAA headquarters, which is located in Virginia, near Washington, D.C. They provided us a very nice Zoom platform and really appreciate their support. And this event is being recorded. It will be posted online after the event. We'll send out a notice to everyone. It should be very stable, but if it somehow got disconnected, please keep trying to reconnect. It should be resolved quickly. And one thing about the security, there's a lot of improvement for Zoom, but if you are still concerned, say for example, you are working with defense contractor, you don't want to use the Zoom app, you can use the browser, version, or you can just dial in. And please don't talk about any, sensitive, information, personal or your work over Zoom. And please sign in your name so people can identify you. You can interact with each other. And later the moderator will tell you, but just mention you can type your question in the Q&A box. And just a few words about Southern California. It's a very exciting area and it's heavily aerospace related. And we have our company doing great jobs. For example, James Webb Space Telescope now with Northrop Grumman, but actually this project was started with TRW, and the very exciting thing is actually D-Wave, has a very interesting connection with TRW, and you can see there's very interesting. So I just mentioned to our distinguished speaker and moderators, panelists, that it's like their home. So welcome home. And we have people working on, defense project, personal Mars 2020 Perseverance, and the helicopter these days, space tourism, Virgin Galactic, Virgin Orbit, SpaceX is right next door. Then we have student doing student rocket launch, passing the common line, and we have a lot of people, Aerospace Corporation, SpaceX, space debris, planetary defense. That's just so exciting. And words about AIAA, if you join AIAA, you can right away use a very great tool called Engage online, and you can start to post your information, chat with worldwide AIAA member and leaders, expert in aerospace. And we keep doing event to keep everybody connected and inspired. Then see what's the great activities in aerospace. Today is one, and this Saturday we'll have a mini conference on new space. And membership is very important, to keep everyone involved, and educated membership is free. And our membership chair, Aldo, Mr. Martinez is working Boeing, is doing a wonderful job. And we also just announced high school student membership, and Ms. Khushbu Patel, who's working with Relativity Space, is doing very wonderfully. She is very passionate in helping the young people. The AIAA national level has been doing major forums and conference like aviation, propulsion energy, and defense, and now we have Ascend and the SciTech. That's very the key flagship programs. And we keep doing events. For example, this is sustainable aviation, electric hybrid aircraft, and you have very top people. This is a national level event at local section. Keep student going, brand mini conference, Hyperloop, and advanced propulsion. And we also, aerospace quantum computing is a very important topic for us. Space architecture, promote equality, for minorities, and we just have an exciting, the first Columbia Space Shuttle launch is fun, and we are going to have a special edition from newsletter so people can share their thoughts and articles. Okay, so with this, I'll turn it to Ms. Susan Davis, who is the marketing lead manager in D-Wave, and she will take it over from here. So welcome, Susan. Thank you.
Great.
Thank you so
well,
much.
Thank you so much, Ken, and thank you to the AIAA for inviting us to participate today. We're very excited to be talking to you. We do have, in addition to our speaker, who will be talking about quantum computing, as well as showing you some live demos, we have our panelists standing by who can answer questions while Victoria is going through her talk. So if you have any questions, either for Victoria at the end or during the talk, please put them into the Q&A box, not the chat box, but the Q&A box, and we'll answer some while we go and some at the end. So I'm very pleased to introduce Victoria. So her full name is Victoria Haran Galiber. She's a senior technical analyst with D-Wave. In her current role, Dr. Galiber works with teams around the world to bring quantum annealing to a variety of groups through seminars, workshops, and conferences. She also does our training. So she's getting all the information about the system out into the world. She received her PhD in discrete mathematics from Arizona State University in 2012 through the U.S. Department of Defense Science, Mathematics, and Research for Transformation Scholarship Program, and more recently completed a master's degree in computer science with a specialization in machine learning through Georgia Tech University. After graduating, Dr. Galiber worked as a senior mathematician with the U.S. Air Force Research Laboratories Information Directorate, and she had a special assignment as the executive officer to the director. She joined D-Wave in 2018 as a research scientist, and she continues to support our sales team through customer interaction and training. So please take it away, Victoria.
Thanks, Susan, and thanks to the organizers for inviting us to be here. Let me just go ahead and share my screen and we'll get started. All right. So I'm Victoria Galiber, and I'm here to talk to you about what D-Wave has to offer and what you can go ahead and get started with today. What are we capable of, and what can you play with and get your hands on right away? So first, I'll go through a little bit of an introduction to what we have available. We'll look at some of our customer applications, and we'll go a little bit into the hardware and software that we have available for everyone to use. And then hopefully for most of our time together, we'll actually have a live demo where I'll run through our LEAP platform as well as some of our code examples to really dig in and see what all of this is looking like and what's going on. So at D-Wave, we're at the forefront of this maturing quantum industry. So we are already supporting commercial applications. We have a busy developer environment with our LEAP platform with over 20,000 developers. And we see entrepreneurs building businesses based on quantum. We have service providers tooling up, incubators and universities producing these quantum startups as well. So on the right, you see just a few examples of this ecosystem that we're all working in. So you can access our systems both through our LEAP platform and AWS Bracket. We have relationships with Accenture, as well as some of these startup incubators like the Creative Destruction Lab out of Toronto. And what we're seeing is that the market is ready. So we have a lot of businesses that have these really difficult problems that they've basically kind of set to the side for now because they haven't been able to solve them with classical methods. Either they're taking too long, or they're too complex, or they're just not a great fit for these classical systems and algorithms that are available. So what we're seeing in this market research is that this 81% of companies have quantum use cases in mind for the next 3 years. There are use cases in almost every industry. So anything that has to do with like optimization is a really great fit, as well as other areas like material science and lots of different use cases out there. And I'll show you where you can learn more about that. We see a lot of different enterprises experimenting with quantum today, both with our hardware and other hardware systems. And it's just a really great time to be in this quantum ecosystem. There's so much interest and excitement about what's possible and what we can do. And this primary driver that we're seeing is competitive advantage. People want to make sure that they are ready for when quantum is ready, so that they have this advantage over their competitors, and they see this efficiency over existing methods. We have a lot of different practical applications of quantum computing, And this is just a snapshot of some of them. So for example, we've been working a lot with this group, Menton AI, that's looking at drug discovery. We've also been working with a Canadian grocery store, Save On Foods, looking at scheduling and logistics. We see a lot of interest in the automotive industry. We've worked a lot with Volkswagen on manufacturing and mobility. And then also in materials discovery, and one relationship is with this company, OTI, that looks at different OLED display methods. So just digging in on one of these, so that manufacturing, logistics, and mobility, again, we see a lot, especially in like the automotive industry. There's a lot of really good applications like traffic routing, planning, scheduling. There's a lot of really hard optimization problems in there that you can take a look at and see how well they fit to our system. So we've had a strong relationship with Volkswagen for several years now, which started as kind of a little research project looking at traffic flow and traffic congestion. So they spent a good amount of time learning how to use our system and mapping this traffic congestion problem. They took real world data from taxis in Beijing going between the city center and the airport, where there's generally a lot of congestion there. And they took a look at this real data and said, is there a more efficient way to route cars across the streets that are available? The problem with current methods is that they're very user centric. So when you're using your Google Maps and it says, oh, there's a traffic jam ahead, you should take this exit, it's probably also telling everyone else in the traffic jam to take the same exit. So you're probably just putting that traffic jam onto another road. Using our system, they were able to come up with a routing plan that evenly distributed traffic across all of the paths so that overall time to the destination was minimized. And it was a really cool proof of concept. It was just a proof of concept, though. So what they did next was at the 2019, there was a big conference in Lisbon. They actually worked with the shuttle buses for this web summit. And they used this, they built up this traffic congestion app and used the quantum computer real time to route these shuttle buses through a very busy area in downtown Lisbon along the waterfront where the conference takes place. And they found some really interesting results, and the drivers were very pleasantly surprised with the routes that they were given. We even have a quote from one of the drivers saying something like, I've been doing this for a good many years now, and it took me on a route that wouldn't normally be the route I would take, but it was faster, and it was a great method to get me to the destination. So what we're seeing is kind of these new applications popping up, and they're actually making their way into the real world at this point. So you can see here on this slide a few different applications in this space where we have traffic routing, airline planning and routing, airports, railways, a lot of these like infrastructure type, transportation type industries. There's tons and tons of hard optimization problems that are really just prime for quantum computing. In particular, we've worked a lot with Denso, Toyota, Volkswagen, as well as a Japanese company called GrooveKnots. So with Toyota and Denso, we've looked at things like optimizing routes around factory floors, efficiently flowing the traffic in their factory so that everything is running smoothly and there aren't traffic jams and there aren't backlogs. They've looked at a few different projects, and so this is just kind of a quick snapshot of one that they were looking at. They've looked at routing, scheduling, lots and lots of different applications there for them. And then Toyota, again, with the University of Tokyo, was looking at optimizing traffic signals for their control system. So, you want to optimize the traffic signals so that you don't have traffic jams. I mean, I think we've all driven in a city where the traffic lights are timed properly and where they're not. And it's definitely a much more pleasant experience to have all the lights synchronized so that you can get where you're going without being stuck in a huge traffic jam. So it was a really interesting project to see how they can use our system to optimize over changing traffic conditions and everything. And then last but not least, the GrooveKnots project. So this really looked at like some city planning things like waste collection. So how are you planning the routes for your trucks that are picking up trash? Is this an optimized route, or are they kind of like retracing their steps all the time? Is there a more efficient way to do this? And they looked at this problem and they said, yes, they were able to. And as you can see here under business value, you see that their CO2 emissions reduced by approximately 57%, and the number of vehicles were reduced by approximately 59%. So those are huge savings for a company that's doing like waste collection or anything else where you have to kind of go house to house. Oh, and then this is the Volkswagen one that I already kind of talked about. So this traffic flow problem. So using our solvers, again, they were able to look at this traffic flow problem and used our hybrid solvers to really scale up these problems from their small little proof of concept to a much larger real world example. So what we have to create all of these applications is really this combination of Advantage and Leap and our hybrid solvers. So Advantage, this is the quantum computer that you always hear. D-Wave has a quantum computer, right? Advantage is our top of the line quantum computer. We released it in September last year, and it has over 5,000 qubits with a greatly increased connectivity. So I'll talk a little bit about what that means when we go to the live demo. But basically, you can fit much larger problems on this system. It's a huge improvement over our last 2000 Q system. Now, Leap, on the other hand, this is our cloud platform that allows you to get immediate access to our quantum computers. So when you run a problem on our quantum computers, you get an answer pretty much right away. There's no like sending it over and collecting results 30 minutes later or things like that. This is you're sending your problem over and the results are getting sent back immediately. It's really fast. And again, I'll run some problems live so you can all see that for yourselves. Now within Leap, we have lots of resources. So things to get you started, like videos, documentation, Jupyter notebooks, code examples, demos, the list goes on. There's so many resources on there that you can really just sign in and dive right in to building applications. We also have an integrated in-browser IDE, which I will show you. So you can code right in your web browser. You don't have to install anything on your system. You can if you want to. If you want to do local development, you can go that path as well. But especially when you're just getting started, you might want to just try it out. You can go right through your web browser. Also through Leap, you get access to 2 hybrid solvers. So we have a binary hybrid solver, which can run problems up to 1 million variables. And then we also more recently released our discrete hybrid solver, which instead of looking at models with just 0, 1 variables, we can now have discrete variables, which has really improved the flexibility of the types of problems that we can solve with our systems. There's also a lot of tools there for collaboration and contribution to the community. So we have a community discussion board where anyone can post questions or answers. There's opportunities to contribute code examples to our collection. There's lots of opportunities there. So especially if you have like students or anyone that's interested in really getting hands-on with the system and learning how our tools work and everything, that's a great way to learn and to really get involved in the community. So here's a bit of a timeline of where we've come from and where we plan to go. So D-Wave has been around for a good while now, over 20 years. And so we started, where everyone starts with quantum computing with just a really small system with, 2 or 4 qubits. And we've consistently been able to scale up the size of our systems to get to the point where we are now. So now we're at the Advantage system with over 5,000 qubits. And we have over 250 of these early applications, like the manufacturing and logistics ones that I highlighted earlier. We've demonstrated a few different customer advantage key metrics that you see here. So for Menton, that was that drug discovery company. They reported 100 times speed up. Save on Foods, that was the grocery store. They reported 500 times speed up. And that Volkswagen project, Volkswagen has a few different problems that they're looking at. They're seeing an 80% reduction in waste. So we're really at that point of starting to see customer advantage where using the quantum computer and using the tools that we have available is improving what customers are currently doing today. So by adding in the D-Wave services, they're able to improve over their current methods. And again, just as I mentioned, you can see here we have this proven ability to scale up to over 5,000 qubits. So qubits aren't the only important thing, right? So there's a lot that goes into a quantum computer chip, as I think we've all seen in some of the press. So we kind of look at this qubits and couplers. So couplers is what's used to connect qubits together. And that's a really important piece of how you can fit a problem onto the chip, right? If they're not connected, then you can't really have them interact with each other at all. So the couplers are a key component as well. So that's really the metric that we use for this scaling. When we went from 2000 Q to Advantage, we did change our architecture so that we have many, many more couplers compared to the number of qubits, which has allowed us to put more and more complex problems onto the system. Now, this Advantage chip, we're really focusing on business. So again, we changed this topology. That's what we call like the underlying map of qubits and couplers on the chip. So we've changed it so that there are more couplers connected to each and every qubit. That allows us to get more compact embeddings of problems onto the chip, and which results in better performance. We'll go into that a little bit when I show you the demo. We also added in a lot more of these Josephson junctions and everything that really goes into making the chip. And I should probably admit right now, I don't have a physics background. So if you have questions on the physics or how the chip is actually fabricated, we can take those down and ask our team later. But my background is math and computer science. All right, and so again, with this performance for business, again, we've got like this chip that's not only larger, but has the greater connectivity. That means larger, more complex problems on the chip, but we're also getting better quality solutions. We're adding in more of these hybrid solvers that can run larger and larger real world problems. You know, hybrid solvers are a really, really crucial component to customer advantage. No matter how big D-Wave makes the chip, it's always going to be a finite size. And there's always going to be someone that says, I need it to be bigger. Well, with these hybrid algorithms, what we can do is we can take classical methods to figure out how to kind of partition our problem into pieces that will fit onto the quantum computer and recombine them to give us a good, valid solution. It's not an easy thing to do, and so we've spent a good amount of time looking at how can we best implement these hybrid algorithms so that we can start focusing on real world sized problems. So to get access to all of this that's where this Leap Cloud platform comes into play. So we have the D-Wave Advantage system, and you access that through Leap. Leap is free for anyone in our Leap countries to sign up. So that's North America, most of Europe, Japan, India, Australia, Singapore. I think that's it. You can sign up for free. And when you sign up, you get 1 minute of quantum computing time, or what we call QPU time. It does not sound like a lot, but it is a ton of free time that you should all take advantage of. And I'll show you just how much that translates to. And so logging into Leap gets you access to all of these resources that I talked about, like the community support, documentation, code examples. There's so much there. And so that it's just a great place to go and try it out for free and see how you like it, see what you can do with it. And here's just a little picture of our in-browser IDE. So it looks very familiar, right? For those of you that have used, like Visual Studio or a different IDE, it should be very familiar and comfortable to use. You can use these tools right out of the box, and you can run some of our code demos right out of the box in your web browser. You can use our hybrid solvers. You can use all of these solvers using our in-browser IDE. So again, you don't have to install anything locally. You can just go ahead and give it a try and see what you think. Now to build programs for our quantum computer, we have our Ocean SDK, the software development kit. So Ocean is built up of a lot of different packages. It's written in Python, and almost everything is open source, so you can see it all on our GitHub repository. You can go check out exactly what's going on. But this is a bit of a high-level overview of what Ocean entails. So starting at the bottom, we've got the quantum computers, the QPUs. And then you may also have some like CPUs, GPUs, you may have like HPC systems that you have access to. These are all different compute resources that you have available. Above that, we have samplers. So like the D-Wave API, that's what we call the sampler that allows you to access the quantum computer. We have our hybrid samplers. So these are our classical quantum hybrid algorithms that will use both classical and quantum resources. And then we do also have in our SDK some classical packages as well, like simulated annealing, so that you can try out and test your code before you run it on the quantum computer. Above that is really your like problem formulation. What is the problem that you're running? And this is where we really focus on this binary quadratic model. You may have seen Cubo. Icing is also a kind of binary quadratic model. But basically, we are formulating our problems so that our variables are binary and all of our terms, like the highest degree you have is quadratic. So it sounds pretty basic, like there's not a lot you can do with it, but there's actually a ton that you can do with it. And for anyone that's familiar with like NP complete or NP hard problems, there's a great paper out there by Andrew Lucas that shows how you can map all of the original 21 NP complete problems to this Cubo or Icing binary quadratic model form. Now, what does that mean? That means these are some of the hardest problems in computer science and math, and you're able to model them in the form that's proper for our quantum computer. So you can run these NP hard, NP complete problems on our quantum computer today, which is really, really cool. Now, above that, we have a few different specialized packages. So if you're working in like graph theory, we have a graph mapping package, which has a few common algorithms in there, like traveling salesman, vertex cover, max cut. There's a few of those common problems that you see a lot in graph problems. Those are already like implemented for you, so you can run them just on your graph as is. And then we also have a constraint compilation package, which is for like satisfiability type problems. Now these green packages on top, this is kind of like where the customer work would live. So you developing your own application, you're going to develop your own kind of software package that sits on top of Ocean for your specific application, whether that's portfolio optimization, traffic flow, or scheduling, or something else completely. All right, so I've mentioned our hybrid solvers a few times. So let's talk a little bit more about what those are. So hybrid solvers, hybrid algorithms are a combination of quantum and classical resources. So there's going to be some classical computing going on, and there's going to be some quantum computing going on. And basically you can see in this little chart here that it's going to like break out a piece of the problem. It'll run classically, some of it'll run quantum. You'll look at it and return a solution. So it's really taking your problem and giving you the best of both worlds in a sense, right? So these are portfolio solvers that are going to run a combination of different algorithms, and it's going to return the best solutions that it found across the portfolios. Now we have a binary quadratic version. So again, this is those 0, 1 variables in your model, and that can run up to 1 million variables. This is a huge problem, right? A problem with 1 million variables. You can do a lot with 1 million variables. And so we're seeing some really great results come out with the binary quadratic model solver. Now, in addition, in October last year, we released our discrete quadratic model solver. This allows us a lot more flexibility in the problems that we're running and how you formulate them. So basically, instead of each variable having to be either 0 or 1, now you could say, well, each variable can take a value from integers from 1 to 5. Or you could say, each variable is a person that I'm looking to schedule for a shift either on Monday, Tuesday, Wednesday, Thursday, or Friday. So basically now you have a lot more flexibility in how you model your problem, and it allows you to kind of think more intuitively about how you're formulating it. And what we're seeing with our performance for these hybrid solvers is that with this quantum acceleration, we're seeing much better solutions coming out, right? And so it's really built for these production applications. That's why we're really focusing on scaling up that variable count and looking at how is it comparing to what's currently in use today. All right, so Susan, were there any questions before I dive into the demo that we should answer first or wait till the end?
The one question was, how many variables can be handled by the discrete solver?
So I believe the like safe bet for the discrete variable solver is 5,000 variables with 10,000 cases. So like your variable could take any of the integers 1 through 10,000. Now I say that's a safe bet. Depending on how complex your problem is, you may be able to run problems that are even larger. It really depends on like how interconnected your variables are and like how dense your problem is. But that's like kind of a safe bound. Good question though. Any others, Susan?
No, that's it.
Okay. All right, so let's go dive in to what we have online that you can all check out. So I'm at our homepage, dwavesys.com, and there's tons of information here before you even sign into Leap. So first of all, if you're interested in exploring some of those 250 plus applications and seeing what people are doing, we have this applications tab on our webpage. And now if I just click on that and head over there, I can actually dig into these different applications. So you'll see that we have tons of different types of products that you can look at here. So there's presentations, videos, papers, case stories, code, or websites. And so a lot of this is actually generated by the customer themselves. So the person who's actually working on the application. And so you can find like published papers to dig into. You can find links to their code repositories on GitHub. So you can go and look and see exactly what they're doing. Or you could watch a video from one of our user group meetings to hear them talking about their application and their experience firsthand. You can filter on different application types. So optimization is a huge area, and it's kind of what we've talked a lot about, but you can see there's also machine learning, material science, algorithms. There's a few different areas in there, as well as you can filter by industry. So here's some of the industries that we mentioned earlier. There's also a lot in like finance is a really big area right now. So I'd really encourage you all to kind of go explore and see what's in here. There's everything from like academic work to like real world use case work from say like Volkswagen that I showed earlier, and kind of everything in between. So there's a lot to see there and a lot to explore. We also have on our resources tab a lot of information. I especially like to show people this developers piece right here. So if you really want to be hands-on, this is a really good place to go to get started. We've got some tutorial videos that will really walk you through how to formulate problems. What does it mean when a problem is embedded onto our system? And how do you use these hybrid solvers that I mentioned? We've got some white papers that talk about these different systems and solvers that we have available. There's some data sheets. And then last but not least, some actual like written guides that show how do I choose a good problem for quantum annealing? What are the characteristics that I should be looking for? How do I formulate that problem? How do I write a program with your software for that problem? And then last but not least, how do I tune the parameters to get the best performance possible out of your QPU? So lots of information there for anyone that wants to get started. It's really, really helpful. But then if you want to try everything out for free, that's Leap. So you can go and sign up for Leap. And when you sign up, you get 1 minute of QPU time free. And if you enter in your GitHub handle, that 1 minute will renew every single month. So you have lots of time to really try your hand at things and see how you like it, how easily your problems might map to the system and what the results might look like. So when you log into Leap, this is what you'll be greeted with. So this is your dashboard. When you log in, you see how much time you have remaining. So I've only used a little bit. On my account, I had 10 minutes, I think, and I've used a very, very small amount. You can see how much of this is hybrid solvers. So I've used about 26 seconds of hybrid solvers time. And if I look at direct QPU total, this is running just on the quantum computer, not with the hybrid solvers. You can see I've run like 2 problems and just used like a fraction of a second. It's very, very fast. And you can see that overall, out of those 10 minutes, I still have quite a bit of time remaining. I've got 9 minutes, 58.6 seconds. Now, if I scroll down, you can see problem status. So you can see all of the problems that you've run in your recent history. You can see if it's pending, it would be blue. If it was canceled, it would be red. And you can look back on some of the statistics from these problems, like what solver it ran on, things like that. And then you can also go and look at your usage. This is just today, so I haven't run anything today. But if I click back to 90 days, you can see, at different periods of time, I've run more and fewer problems, right? And then last but definitely not least, this is your list of available solvers. So everyone that signs up will have access to these 4 solvers right away. So we've got 2 hybrid solvers that I mentioned, the binary and the discrete. And then we've got 2 of our quantum computers online. So the Advantage system, that's one with over 5,000 qubits. And then the 2000 Q lower noise system. So for people interested in doing like physics experiments or like material science type stuff, you might need the lower noise system. So we've made that available as well. Now let's go run some code. Let's run a problem on the quantum computer. So up at the top, I'm going to go to resources. And this is where there's tons of information on here. So really encourage everyone to explore here. But I'm going to go right to our code examples. So the Ocean code examples, this is our collection of code examples. And here we have all different examples that range from like puzzles like solving Sudokus to academic problems like max cut, all the way to real world problems like you can see nurse scheduling here. So I'm going to open up one called max cut. And so here it is. So when I click on maximum cut, I'm greeted with a full problem description of what this problem is. So the max cut problem, you have a graph and you want to split the nodes in this graph into 2 sets. In this picture, it's like the white set or the blue set. And you want to split them into 2 sets so that you have as many cut edges as possible. A cut edge is these dashed ones where the endpoints are different colors. So they go like between the 2 sets. So if I split the 2 sets up completely, these edges would be cut. So you can see for this one graph, here's some different partitions that you might find, each with a different cut size. So this one here has 2 of these dashed edges. This one here has 3. And this one here has 5. And for this problem, the maximum is 5. There's no way to cut all of the edges. So we can formulate this problem as a binary quadratic model or a QUBO. And that formulation is fully described here in this README. So for anyone that's interested, you can come back here and read how this is formulated. I'm going to go out and open this in our IDE. So I'm going to load this in the LEAP IDE. Now, when you load an example in the LEAP IDE, it takes a couple seconds because it's setting up a virtual environment with our Ocean Software Development Kit installed and ready to go. It's also linking to my LEAP account so that I have access to those 4 solvers that were listed there. And it's basically setting everything up so that I can run this code with the click of a button without having to install anything or do any sort of setup. So when it first opens, you see that this is the same exact README that we saw on the last page. And on the left here, I have a file browser. And I'm going to open up maximumcut.py. That's the Python file. Now, this is written with our Ocean SDK. And most of our Ocean programs have kind of the same flow. You're going to import a bunch of packages. You're going to set up your problem. So in this case, it was that graph that we saw the picture of. I'm going to set up my QUBO or binary quadratic model. We do that using a dictionary in Python. I'm going to send it over to the quantum computer. I can see here this is D-Wave sampler, which means I'm running it on the quantum computer. This is not a classical. This is directly on the QPU. And then it's going to print out the results for me to see and make some pictures. So let's just go ahead and run this and see how it goes. So it's going to pop up a terminal at the bottom, and it will run my problem on the quantum computer that's in Burnaby, so just outside of Vancouver, British Columbia. And there's the results, right? So that's how fast it is. When you sign up for a free account and run problems on our quantum computer, that's how fast it is. You get access right away. So here you can see our system is probabilistic. So we run it, 10, 100, 1,000 times for one problem, and we get a selection of samples for our solutions. And we look at them to choose which ones are the best ones. So for this problem, as I mentioned, the optimal solution was 5, so cut size 5. And you can see here, if it's not too small on your screen, that we've got 4 solutions here that have that cut size of 5. So we ran this problem, I think it ran 10 times, and we got 4 solutions here that are all optimal solutions, which is really, really cool. Now, one of our really cool features that we have is our problem inspector that allows you to see how your problem actually maps onto the physical chip. So I'm just going to add that in. So I just import dwave.inspector. That's the package where it lives. And then below the line where I'm actually sampling my QUBO, I add in dwave.inspector.show and give it the response object. We've got a great YouTube video that covers using the problem inspector and adding it to your code. So feel free to check that out if you want to make sure you get all these commands down, because I know it's tough on a Zoom video. So now when I run this, it's going to bring up the problem inspector on the right side of the window. And this is our problem inspector. So when it first opens, it brings up a tour. So you can like click through and be shown around everything that's there. And then you can look at your problem. Oops, not sure why that happened. There we go. All right, so I'm just going to start using the inspector, and let's see what we've got here. Okay, so here's this problem. Looks pretty similar to the pictures that we saw. So this is our graph. This is our problem that we're looking to partition. And you can see just instead of blue and white, we've got yellow and white for our sets. All right, so over here on the right, this is showing me my samples sorted by energy, sorted by like how good these numbers are. Our system minimizes, so the numbers to the left are going to be the best ones. So as I click on each one, you'll see the colors on the nodes over here change as the solutions change. So here I can kind of visualize the different solutions that I have for my problem. To see how this logical problem, that's what we call it, the logical problem, maps to the physical chip, I can up here on the top right click on 2, and I can see exactly how it embedded onto the QPU. So zooming out, you can see the full size. This is actually our 2000Q chip. Zooming out, it's a little dark, but you can see like this is our full size chip, and we just used this tiny little area in here. So there's a lot of space on that chip to run some problems. Now I can see which variable went to which qubit. So this variable mapped to this specific qubit. And there you go. And then last but not least, here we have a chain. So here we've got, a set of 2 qubits that are working together to represent this one variable. As you can see on the chip, we don't have like all-to-all connections. So to fit this problem onto this type of structure, you sometimes have to represent variables by groups of qubits to kind of stretch it and make it fit onto the chip. And so that's what you're able to see here. So that's one of our problems that runs direct on the QPU. Now let's wrap up with one of ours on the hybrid solvers. So I'm going to close this, and I'm going to go back to the collection of code examples, and there's a new one that we have called airline hub locations. Now this problem is looking at a set of 25 different airports, and it's saying, okay, if you're an airline and you have these 25 airports, and you've got costs for operating flights between any 2 of these airports, you've got passenger demand between any 2 of these airports, how should I choose which 3 of those 25 should be hubs? where do I want everyone to connect through? And there's also some discount if you have flights between hub locations. So how can I optimize so that I minimize my cost? How do I choose those 3 hubs out of 25 different airports? And that's what this problem is looking at. So again, let's load this in the Leap IDE. And while that loads for a second, you can see when we run it, we'll be presented with, there's a little GIF that shows the different solutions. And so you can see like the cost for each of these solutions. And it's kind of cool to see if it really like meshes with reality. Are these airports actually hubs or not? And a lot of times for some of the best solutions, we do really see it kind of fitting what we see in the real world. And there's more about the problem formulation as well as a reference for where the problem came from. So let's look at our example. And in here, again, on the file browser on the left, I'm going to go to demo.py. And here you can see I'm running my Leap hybrid DQM discrete quadratic model sampler. Okay, so this is going to run that problem with the 25 airports. I've got some CSV files that have information on cost, just like straight numbers for the cost, as well as passenger flow or demand between any 2 cities. These are all stored as a matrix. And so let's go ahead and run this on the discrete quadratic model, the hybrid solver. And so when we run this, again, you'll see the terminal pop up and it should tell us what it's doing at each stage. So first, it's building our scenario with these cities. It's building the DQM. It already ran the hybrid solver. Now it's interpreting the solutions to make those pictures to figure out, which solutions are feasible. And then it's putting them together to make that GIF. So here's the feasible solutions that we got from the discrete quadratic model, the hybrid solver. And you can see them sorted. The first one is the lowest cost, so it's the best one. And so we're seeing Baltimore, Chicago, and LA being our 3 hubs chosen out of the 25 cities. So let's look at the different solutions that came up. Let me close these first. If we open up this GIF, we can see the solutions that the hybrid solver was able to generate for this problem. And it'll just cycle through them all for you to check out and see what they look like. And then we can look at, that's the best solution found. We also get kind of a static image of the best solution found for you to analyze. All right, so I think I've pretty much, I've got some time for questions now, if we have any questions.
Okay, we have a few. First, so quantum computing can give you a different answer every time you run the program?
Yes. Yeah, so it's probabilistic. So when we run a program, we set how many times we want it to run. So number of reads is the parameter. And so generally we'll do it like 100 or 1,000 or 10,000 times to make sure we're really giving it a fair shot. It is probabilistic. So if you just run it once and then you run it once again, yeah, you'll probably get a different solution unless it's a really, really simple problem.
Okay, thanks. One of the things I'll mention is that one of the things that a quantum computer can give you is the ability to find not just the optimal solution, but many good solutions. And depending on some of the trade-offs about cost and time and that kind of thing, there's often a lot of business value in having lots of good solutions as opposed to just the one that is kind of the optimal.
Yeah, that's a great point, Susan.
How do we run a quantum annealing problem using LEAP? Say similar to what we run a simulated annealing problem with minimal changes in code structure.
So it would depend on which software you're using for simulated annealing. If you're using the simulated annealing solver that's in our Ocean SDK, then you really just have to change like 2 lines of your code. It's set up so that these solvers are pretty interchangeable and you don't have to change huge sections of your code.
Okay. The next one, the quantum chip is divided into the areas with connected points, qubits. So the logical program should fit this number of 8 qubits.
So yeah, I mean, so the topic of embedding and how your logical problem fits into the quantum computer is a pretty complex topic. Basically, you have to figure out, it doesn't have to fit into like each of those 8 qubit tiles. It has to fit into the whole chip. So you've got a little bit more leeway. Like I think for our 5,000 qubit chip, if you had like your logical problem had every pair of nodes had an edge between them, like in that graph we showed, you could have a graph up to like 119 nodes. But most problems don't have like all of those connections, so it's a little bit easier. Yeah.
Okay. Could you mention some of the aerospace problems that would benefit from your systems and quantum annealing?
Yeah, so a great place to look would be the work that NASA's done. So NASA has done a lot of work. So if you go back to our homepage in that applications page and you search for NASA, they have a lot of work here. So that would probably be the first place I would suggest looking. And I think they've actually also, they've written a couple of papers. I think if you look on like archive that are more like survey papers that look at applications and not just over like our system, but all of the like gate model and annealing as well. That might be a good place to look to get like a broad survey.
Okay. Let's see. Great presentation and cool opportunities. For the airplane problem, how is the best solution paired against parallel computing? Have you heard about quantum meteorology? And if so, do you have a good resource or POC and data standards for that data? That's a lot of questions.
Yeah. So for the second part, no, I haven't heard of that yet. So yeah, feel free to like look me up on LinkedIn and send me some info if you have anything on that. For the first question about like comparisons for this, so this code right here is actually pretty basic code. It's not really super optimized or anything. It's more of like an educational tool. And you'll see that like the paper referenced is actually from like 1987. So this is actually kind of like implementing the basic model so that others could build on top of it. So for your specific problem, you may have more constraints, you may have different constraints. So we're kind of like, here's a basic like vanilla model that you can customize for your needs. So there hasn't been like a ton of testing or anything because it's not really like cutting edge or anything.
Okay. A follow-up on the question about quantum annealing. I don't remember you mentioning any solver using quantum annealing other than Cubo and discrete Cubo. So how do we use quantum annealing from Leap or Ocean's SDK?
Oh, so when I talked about like the solvers that are available, so at the bottom, so these QPUs, these are quantum annealers. So you model your problem as a QO to run on the quantum annealer. The hybrid solvers, you're modeling it as like a QBO or a discrete quadratic model, and parts of it will run on these quantum annealers. But basically everything that we're doing here is quantum annealing.
Okay, and last question, I'm not quite sure I understand it, but maybe you will. Can you comment on the advantage of quantum annealing like stabilities, noises, so people can appreciate it more?
I mean, so one of the advantages that I personally see for quantum annealing is so you model your problem as this QBO, and when you run it on the system, it's basically just like one operation. It's one anneal, and you get one of those samples back, and then it does another anneal, and you get one of those samples back. Whereas when you look at like the gate model kind of format and how you model your problem, you have kind of a sequence of circuits, and you have to maintain the coherence along the sequence of circuits. Whereas ours is just like one operation. So I think kind of what you're asking me to talk about is that like we're not as susceptible to like noise and those coherence issues because we really just do the one operation and you get the answer rather than having to maintain across this sequence of circuits.
Okay, well, I think we are at the end. If anyone has any additional questions or want some more information, if you send an email to sales@dwavesys.com, that's DWAVESYS.com, it'll come to me and I will get it to the right person to answer it. As Victoria said, we really encourage you to take a look at our website and sign up for LEAP and try it yourself. There's a community where you can get some help in there. Victoria is also doing a training class in June. The way it's structured is it's over the course of 5 days, but there are, all of it is online and virtual, so you can do it at any time that's convenient. And then Victoria will have office hours so that people can get help. So again, if you're interested in finding out more about that, again, send an email to sales@dwavesys.com. So with that, I'd like to thank Ken. I'd like to thank AIAA. We're really excited to have been here today and hope you've learned a few things. And we look forward to further discussions if that would be appropriate. So thanks very much. Thanks, Ken.
Yeah, thank you, Susan. Thank you, Victoria. Thank you, Alex. This is fantastic. So stay in touch. We'll hopefully you'll come back again, to tell us more about your great progress and product services. Yeah, thank you very much. Thank you everyone for joining us today. If you have any question, please, as Susan said, contact her, or you can forward to us, and we'll direct to Susan. Okay, thank you very much. This is a great topic, very exciting. So really appreciate. Thank you very much once again, and stay tuned. And this Saturday we have the New Space mini conference. Please look into it and please join us. Have a great day, and thank you for everything. Enjoy the week. Thank you. Bye bye.